Hi, this is week 11 lecture. In this week, we will talk about the heat exchangers and to see how many types of heat exchangers are available, and what kind of method of analysis that we need to use to find the heat transfer in these devices. But before we start the topic, we need to complete last week examples, because last week we've been talking about the heat transfer by convection, by forced convection, internal force convection, and we were up to the an example that describes the heat transfer in constant heat flux surface. So remember, we were talking at that time that we had two types of analysis in forced convection. Internal forced convection depends on whether we have constant heat flux or constant temperature. And I just recall the equation that we used last week. So this is the case that we have constant surface heat flux, and we said that in case that we have constant heat flux, so easily we apply the Newton's law, which is the equation in the red frame here. This is Newton's law describing the heat flux equal to H, heat transfer coefficient, multiplied by T surface minus fluid temperature. Tm is the average fluid temperature at any section of the pipe. So if I cut anywhere there, this is my Tm. So if I know the Tm at a certain location in the pipe, I have the surface temperature given by Ts, and the constant heat flux is anywhere at the surface is the same. So Q dot S is the constant or the heat flux anywhere on the surface. So this is the equation that we need to use. In case that we don't have constant heat flux, but we have constant surface temperature, so the solution will, or the equation will be different. The difference here will be because the difference between surface and fluid is not constant. As you can see in this graph, this is the delta T between delta T here. This is the delta T, which is Ts minus Tm. And it's almost like, you can see anywhere across or along the tube or the pipe, we have almost the same delta T. Now, if you go to the other case, which is the one that has constant surface temperature, as you can see here, the surface temperature along the pipe is the same, constant. But delta T, you can see here at the beginning, delta T is bigger than delta T at the end of the pipe, which is the delta T here is the difference between the Ts minus temperature of the fluid. So we have to approach different, we have to have different approach to find the Q dot. So as you can see here, Q dot also following Newton's law, but the difference here with delta T. So we have H is the heat transfer coefficient, that's the same. We used in previous equation. As also, the surface area is the same, nothing changed, because this is the surface area of the cylinder or the tube or the pipe. But delta T here is different. So delta T is the logarithmic mean temperature difference. And we have to follow this formula in order to find the delta T ln, or delta T logarithmic mean temperature difference. And as you can see here, this is the final form of the equation, and delta TE minus delta TI divided by ln delta TE divided by delta TI. So once you know delta TE from this equation, and you know the delta TI from the other equation, then you just need to substitute them in the above equation. So this is, in brief, how to find heat transfer in these two cases. Now, let's apply this on the example. So the first example here we have is dealing with constant surface, constant heat flux on the surface. And in this example, water is heated from 15 Celsius to 65 Celsius. And we have been given the internal diameter of the tube. So the tube diameter is 3 centimeters, as you can see, and the length of the tube also given. The tube is actually equipped with electric resistance. So what does it mean here? That there is electric resistance around the tube, like a wire around the tube. And this wire actually is a resistance. And when the current flows inside through this wire, then it will create heat. And the heat will be constant because it's the wire is distributed along the length evenly, so that we get same amount of heat flux anywhere. So the requirement here, actually, we also given the water volume rate. As you can see here, 10 liters per minute. We can use this volume flow rate to find the mass flow rate, because we need the mass flow rate when we want to find the Reynolds number. So now the requirement here is to determine the power rating of resistance, and also we need to estimate the inner surface temperature of the pipe at the exit. So we have two requirements here. We need to find the power of this wire or this resistance. And as you know that this resistance, when we release heat, when the current flows in the wire, it will release heat. So the heat will, all the heat will go through the thickness of the tube, or across the tube wall toward the water, to heat the water. So all the heat coming from the wire will be observed or be gained by the water. So, which means that the heat Q dot by the electric resistance will equal Q dot gained by water. So therefore, if you know that this part, if you know this, how much heat we gained by the water, it will be the same as the heat, or the power rate of the resistance. So we are answering the question. If you can find this part, this part actually equals the power rating of the resistance eta. Okay. So now to start solving the problem, as you know, this is, first of all, this is internal flow. So it's forced convection, internal forced convection case. So because it's internal convection, we need to ask ourselves, is it constant heat flux or constant surface or constant temperature, surface temperature case? So as you can see, it is constant heat flux. Therefore, we can use the first form of equation presented before at the beginning of the lecture. So we will find out this very soon. So the first thing that to solve these questions, we need to find the property of the fluid for each case. So for example, in this case, we have water, and the water temperature is different, like from the at the inlet and different from the at the exit. Therefore, we need to take the average of the water temperature between inlet and exit, and we can find the average temperature, which is 40 Celsius. And then we can take this temperature to the table, go to the tables, and table A15. This table will give you different properties of the water at this temperature, such as the distance, the density, the conductivity, and kinematic viscosity, specific heat, and Brownian number. So all these properties are required in our calculation. So you need to get this before you do anything. Then also I need to find out the surface heat transfer area, and heat transfer area, because we mentioned before, because we have circular case, we need to find the heat transfer area of a cylinder. So which is the parameter multiplied by the length. So pi d multiplied by the length L, then we can get AS. So now we have the surface area. The other requirement, we need to find the flow rate, because as you know that we need, when you want Reynolds number is the velocity multiplied by the diameter divided by the kinematic viscosity. And this actually, the velocity is not given here. So we need to find the mass flow rate, then to find also the velocity as well, to find, then to know what's our Reynolds number. Okay. Now, the heat transfer to the water, as we said before, the heat coming from the electric heater gained by the water. So because of we are applying energy conservation, or the first law of thermodynamics, the heat added must be heat released, or heat gained must equal to the heat released by the electric heater. So based on this concept, we can get the heat gained by the water if we apply this equation. So Q gained by the water basically is the mass flow rate of the water multiplied by Cp, specific heat of water, multiplied by the difference between inlet and exit of the water. So this is actually what what the water gained, the heat energy gained by the water. And we find out this is the amount of kilojoule per second, or kilowatt gained by the water. And exactly what this is, which is exactly equal to the electric heater power, or the electric heater or resistance power. So the power rating of the heater will also equal 34.6, as you can see here. Now we need to find the surface temperature of at the exit, TS. As you know that surface temperature is not the same, because we have now constant heat flux case. So surface temperature at the beginning is different from the surface temperature at the end of the tube. So we can apply this equation, and we can solve it solve it for TS. So as you can see, TS here is equal to Tm, which is the fluid temperature, plus heat flux divided by H. So now our duty is to find this value, H. We don't know H. Now to find H, as we said before, we need to refer to the value of Reynolds number. So Reynolds number, we said before, Reynolds number requires velocity. So velocity here is equal to the volume flow rate divided by the cross-sectional area, AC. the cross-sectional area of the tube. And we have been given this in the example. So we know the cross-sectional area of the tube. So you just need to divide the volume flow rate, divide by the cross-sectional area to get the velocity meter per second. Then we can use this velocity in Reynolds equation, Reynolds number equation, and find out the value of Reynolds number. And as you can see here, Reynolds number is 10,760, which is much greater than the 4,000, our limit to turbulent flow. So we start turbulent flow after 4,000, fully turbulent flow. So 10,000, we have fully turbulent flow after 4,000. So now we have 10,000, which is much greater than 4,000. Therefore, the flow here is turbulent. So now we know that the flow is turbulent. We just need to choose the right equation of Nusselt number. And if you refer or revise the last week lecture, you will find that for turbulent flow, Nusselt number is following this equation. And this equation has Branham number to power n. Power n either 0.4 or 0.3. If it's heating case, then we use n equal to 0.4. If it's cooling case, then we use instead of 0.4, we put 0.3. Just refer to the equation, please. So in this case, we have heating process. So we use 0.4, we substitute 0.4 in this equation, and we get the Nusselt number. Then it's quite easy then to find the H. H value is 1,462. Now we found all the unknowns required to find the TS value. So we just need to substitute the value of H in the equation, in TS equation, and get TS value, which is 115. All right, so that's one case. Now the second case is the when we have constant surface temperature. This example about this constant surface temperature case. As you can see here, we have square duct, and given the cross section dimensions, which is 0.2, 0.2. So we have equal sides, and we have air is flowing inside this duct. So we have where air in and where air out. We are only given the temperature of the air inlet to the duct. We don't have any information about the temperature at the exit. The duct is observed to be nearly hydrothermal at 60. So the temperature, we set constant along the surface, anywhere at the surface is constant at 60 Celsius. We need to find out the exit temperature of the air. Okay, so again, we ask ourselves, is this what's the type of heat transfer here? Of course, it's internal convection, forced convection, and because in internal we have two cases, either heat flux constant or surface temperature constant. So this case is surface temperature, constant surface temperature. Then we know that we have different formula to use. Now to start solving the problem, again, we need to get the properties of the fluid. So air is our fluid here. We need to go to the right table, but we need to use the temperature of the air. Now we have the air temperature here, as you can see, is 80. And I mentioned before that we need to find always TF, because to have more accurate values for the property of the fluid, we need to use TF, which is TF here is the T of the fluid plus T surface divided by 2. Okay, But because here, so Tm plus Ts divided by 2. So Ts 60, Tm is 80. So this gives us 70. Yeah. Now we can take this and go tables and find out the property. You'll see that they use 80 here. It will give you almost same values, but to be more accurate, it's better to have T-film because this is the more accurate case that for any fluid. For air, the difference between 80 and 70 is not big, and you will find that all these properties doesn't change much between these two temperature values. But for consistency, make sure that you use T-film better than getting one temperature of the fluid, because depends on the question and depends on the temperature of the fluid and the surface temperature of the tube or the duct. Okay, so now once we have these values, we can easily find Rayleigh number. Same thing we did before, but in this case, because the duct is square, it's not circle, so the diameter of the duct, of course, is not 0.2. We have to have different approach to this. We have to find what we called before hydraulic diameter, and in this DH represented by this formula or this rule. It's 4 multiplied by the area, cross-section area, divided by the perimeter. So, which we conclude after, like, we simplify the equation, it is actually DH here is equal to A. But if we have different sides, then DH will not equal A. So you need to apply this rule to find what's the DH. Okay, the hydraulic diameter of the duct. So now DH is equal to A, which is 0.2. That's one thing. So now we know our DH. We can use this then to find our Rayleigh number. Right, so Rayleigh number here is 35,765, which is again much greater than the limit for turbulent flow, which is 4,000. Now, after that, you have turbulent flow. So now the value is much bigger than this limit. Therefore, our case is we have turbulent flow here. So in turbulent flow, again, we have the equation mentioned before, but before we have that, this is the equation actually we presented before, but now, as you can see, we have chosen different value for N. Brannan number to power 0.3. In previous case, it was 0.4 because we have heating. Now, in this case, we have cooling because the hot air, the air entering the duct is higher, temperature of the air entering the duct is higher than the surface temperature. So you can see here, surface temperature 60, the air temperature is 80. So therefore, the heat will be, transfer will be from inside to outside. So, which means that we are cooling the air. We are losing heat from through the duct, which means that it's cooling case. So in cooling case, back to this equation, we have to choose the power 0.3, not 0.4. So we substitute the value here and find out the Nusselt number, and then we can find the H value. Okay, and then once we find the H value, we can substitute this H in the equation presented before for constant surface temperature and to find TE. So TE is 71.3 Celsius at the exit. So the temperature of the air at the exit drops from to 71. So the inlet was 80. This is the inlet of the duct, and the exit at the duct, we found it is 71.3, which means that we were losing heat while the air is flowing through the duct. Okay, so this is the exit temperature of the air. All right, and to find out the heat transfer, again, because it's a constant surface temperature case, we need to find delta Lin, logarithmic mean temperature difference. As you can see here in this equation requires H value and requires surface temperature, and also requires the delta T Lin. And delta T Lin we mentioned before, because we have different surface temperature, difference between the inlet and exit, fluid temperature changes from between inlet and exit, while the surface temperature is constant. So we always have delta T varying along the tube or along the duct. Therefore, we need to follow this equation to find delta T Lin. So delta T Lin is now minus 15. We use this value in this equation to get the heat transfer through the duct. So this is the amount of heat, kilojoule per second or joule per second, we lose when the air flows through the duct. Okay, so by this, actually, we finish the example of week 10. So we'll start now with week 11 topic. As we mentioned before, the topic is about heat exchangers and types of heat exchangers. Okay, so the heat exchangers, we have different types of heat exchangers available in the industry. But before we go through all these subtopics of this lecture, I just want to give you a quick definition of the heat exchanger. As you can see in this figure, heat exchanger is a device that allow the exchange of heat between two fluids. Most likely it's different types of fluids, sometimes the same fluid. Like if we have water from one side, we have oil from the other side, or we can have the same fluid, water and water, cold water and hot water. But in most of the cases, we use the heat exchanger to heat a fluid by using other type of, by using hot fluid from the other side. So as you can see here, we have we have a fluid entering this heat exchanger, and warm fluid and cold fluid. So from one side, we have warm fluid coming inside the shell here, leaving from the lower exit, while there's a tube in the middle of the shell here. This tube allow cold fluid to enter, and we can heat this fluid by allowing this to pass through the tube here. So when the fluid flows inside the tube, it will gain heat from the warm fluid and then leaves at the exit with different temperature. So we have temperature here of T cold inlet, and we have here T cold exit. And T cold exit actually will be greater than or bigger than T cold inlet because we are heating the fluid. While in this case, warm fluid T, the warm fluid in and T warm fluid out, we will find that T warm fluid out would be less than the inlet of, because again, this is where we lose here. We lose heat from the warm fluid, this heat gained by the cold fluid. So the temperature will drop down. Okay, so that's the definition of the heat exchanger. Now, different types or different applications. We can find this in heating and cooling systems or air conditioning systems in buildings. We can find heat exchangers in chemical processing. Also, we can find heat exchanger in power production, in power plants. You remember we mentioned this before in like the lecture 1 or lecture 2. We've been talking about the energy systems, and we said that in power plants, we have condensers, we have hot water or heat exchangers for in the boilers. So many types of devices or different types of heat exchangers. So this is like just an example of different applications. Now, the types of heat exchangers, the most popular one is the double pipe heat exchanger. The double pipe heat exchanger has two forms or two design. Well, the first one is we call it parallel flow, and as you can see, both fluids, the hot fluid and the cold fluid, both of them entering from one side, from the same side. Say from this, in this case, we have both of them entering from the left side, and both of them leaving the heat exchanger at the right side. So we call this parallel flow. And you can see here in parallel flow, the inlet of the hot fluid, THI, and inlet of the cold fluid, difference between them is quite big. While at the inlet, while at the exit, as you can see here, the T hot fluid exit and T cold fluid inlet exit, the difference between them is small. So this is in parallel flow. In counter flow, the case here, we have hot fluid coming from the left side, while the cold fluid coming from the right side, so opposite to the hot fluid, and therefore we have opposite direction for the flow. So the cold fluid is coming this way, while the hot fluid is coming in the other direction. And as you can see here, difference delta T between them, in this case is between inlet, between hot and cold, are almost the same along the tube. So T hot in, while this one is T cold out. And here T hot out or exit, here T cold inlet. And the difference you can see here, it's not as big as in the first case. So these are the two types of double pipe heat exchanger. So this is one type of heat exchanger. The other type of exchanger is the cross flow heat exchanger. And in this heat exchanger, the two fluids move perpendicular to each other. So there's one side here, a flow coming from this side, normal to the pipes. So in the pipes, we have different fluid. So for example, we have here water. So water flows inside these tubes, while we have air coming normal to these tubes to cool the water. In this, like, we have different applications for the cross flow. One of these applications is the radiator in the vehicle, in the cars. In most of the cars, we have a water cooling system to cool the engine, and radiator actually has similar design of the cross flow heat exchangers. Okay. The third type is shell and tube heat exchanger. And as you can see in the shell and tube, we have big shell, and inside the big shell we have many pipes staggered inside, and these pipes allow the flow go through these pipes. So the flow is coming from this side, for example, and divided into sub tubes or sub passages. And as you can see, the flowing inside here, sorry, this is like in this case, we have two cases here. So we have small pipes here. You can see the flow inside these pipes, while in the other side, we have different fluid coming from this side, and this fluid is going around this shell and leaving from this point. Okay, and then there will be heat exchange between the red and the blue color fluid to get the outlet temperature at this shell and tube exchanger. So probably, like, say, for example, the red one here is the hot fluid. The cold fluid coming from this side to leave with higher temperature at the exit here, while we have hot fluid coming from this side to heat the cold fluid. Okay, that's the shell and tube exchanger. The last one here we're going to mention is the plate and frame heat exchanger. And in the plate and the frame heat exchanger, the hot and cold fluid flow is in alternate passages. So as you can see, we have red and blue color. In between them, in each one of them, there has different fluids. So the red one has, let's say, the hot fluid. The blue one has the cold fluid, and they can't mix together. But they have a special passage, special way to go through this heat exchanger. So the hot fluid coming from this side, it only fill the red plates or red spaces, while the cold fluid only fills the blue plates spaces. and as you can see, we have better or more effective heat transfer, because each cold fluid is surrounded by two hot fluid plates. This will increase or improve the heat transfer efficiency. Okay. Now we come to the method of calculation of the heat transfer through or inside the heat exchangers. And as we mentioned before, the most popular one is the double tube heat exchanger, which has two tubes inside each other, and the heat will be transferred from the hot fluid to the cold fluid. So, for example, here in this figure, we have the cold fluid at the outer tube, while the hot fluid inside the inner tube. Now to simulate the thermal resistance of this case, it will be quite similar to what we presented before in thermal resistance lecture. Remember before we mentioned that if we have circular tube, we can always represent the thermal resistance by these three resistor or thermal resistance. The first one is represents the hot fluid thermal resistance, relates to the heat transfer coefficient of the hot fluid in the inner side of the tube, while at the outer side of the tube we have the cold fluid has also thermal resistance, relates to the heat transfer coefficient of the outer fluid. So we have this one, RO and RI. In between, we have the wall. So the tube wall can be represented by the thermal conductivity of the material. So our wall here represents the effect of thermal conductivity as well as the thickness. So you know that, remember before, the conductivity, the thermal resistance of due to thermal conductivity is delta X divided by K A. Now, if delta X is very small, then we expect R to be too small as well. So sometimes, in most of the cases, they say we will, like in the example, they tell us that the thickness of the wall is very small, the thickness of the tube is very small, therefore you can neglect R. So if this is the case, then you don't need to include the R wall. So the only two thermal resistance is the Ri and Ro, which relates to the heat transfer coefficients of the hot and cold fluid. So this is one case of overall heat transfer coefficient. We have other cases, we'll come to it very soon. But if we have in heat transfer or in heat exchangers, they don't refer to the R total. You remember we said before, we said the R total thermal resistance, the total thermal resistance of this system is equal to Ri plus R wall plus Ro. So this is our total. So you can use this using Newton's law. Q dot is equal to, you can say delta T divided by R. Okay, so this is, or multiplied by A. So R total can be found from this equation. And in heat exchangers, they, instead of using R total, they use U value. So they said U, which is the overall heat transfer coefficient, is equal to 1 over R total, which is the same thing. So then you can represent the Q dot in terms of U, not R. So we can say Q dot is equal to U multiplied by A multiplied by delta T. Okay, so but both of them have the same, will give you the same answer. But this is what they used to use in heat exchangers. So this is the equation used in heat exchangers analysis. So now we have other cases actually in heat exchangers thermal resistance. These cases are due to the fouling factor, and I'll explain what do we mean by fouling now. But before I go there, just give you this table, show this table, which gives you range of U for each type of heat exchanger. We will not use this table to find U, of course, but you can, it's a measure for you to let you know whether your U value is correct or not. So for example, if you found U for, let's say, water to water heat exchanger, both fluids in the heat exchanger are water, and you found U not in this range, then there must be something wrong in your calculation. So you need to check it again. So this is just give you a guideline for you to check whether U value that you have is within the range given in this table or not. Okay. But we go to the fouling factor. We said that when we run the heat exchangers for a long time, for example, for let's say years, after let's say 5 years, there will be some accumulation of deposits on the tubes, especially when we are using fluids which they are not pure. For example, if I'm using, for example, river water or ocean water to cool a condenser in a power plant, this, like the ocean water or the lake water or the river water, is not pure 100%. The purity is not high. Therefore, there will be some deposit on the tubes, and this deposit creates a layer, extra layer on the top of the tube, which makes the extra resistance, thermal resistance to the heat transfer. And this table shows the R value for, which is the represent the fouling factor resistance for different types of applications, heat exchanger application. But then how to include the RF in our equation, our thermal resistance equation. So this is the R equation, and as you can see, we said R has the fluid thermal resistance, inner fluid and outer fluid thermal resistance, and also we have the wall thermal resistance. And as you can see, we added to this equation the two parts here, the two terms, which represent the fouling factor terms, the thermal resistance of the deposit on the tubes from inside and outside. So this is inside, this is the outside. We added to the thermal resistance equation, and we get the thermal resistance or total thermal resistance, including the fouling effect. Right. Okay. This is just a close picture about of a furnace. In this picture, as you can see here, there are tubes here. This is a power plant furnace. The power plant here using coal to generate heat to boil the water in the furnace. And because we are using coal here, the carbon deposit or carbon particles creates a layer on the top of the tubes, as you can see. And this layer, it's actually a resistance, a thermal resistance to the heat transfer. So leaving this layer long time will reduce the efficiency of the boiler, and then, which means that we'll lose energy and lose money at the end. So there must be maintenance from time to time to remove these layers from the boilers. Okay. Now this question here actually is a simple calculation for double tube counterflow heat exchanger. As you can see here, we have counterflow, so the hot fluid coming from this side, while the cold fluid coming from the other side. So we have hot oil and we have cold water. And we need to find the overall heat transfer coefficient of this heat exchanger. right? So we know the diameters of the inner and outer tube. That's already given. So now we need to find heat transfer coefficient. So we'll do the same thing. We need, first of all, we need to find the properties of these two fluids based on the temperature we have. So the property of water, we need to find it at 45 Celsius, because the water, the average water is already given. As you can see here, the average water, we said average water temperature, then we can use this as an average. Take this value to the table. We don't have other value. So this is the average temperature of the water and the average temperature of the oil. So both of them, these two temperatures, we can enter the tables with these two temperature, table A15 and table A19, and find out the properties of these two fluids. And then, because in the question here, they said neglect the thickness of the inner tube. So this tube has a thickness, and they said the thickness is small, so just neglect this thickness. And therefore, if we neglect the thickness, then the equation of the thermal resistance will be reduced to this. We will not add the thermal conductivity effect because thickness is too small. So we reduced it to this. So only the effect of the inner fluid heat transfer coefficient and the outer fluid heat transfer coefficient. Right. So now to find out each one of them, the HI and HO, we need to find the Reynolds number, and then we need to find the Nissot number. Based on Reynolds number, we can find Nissot number. So we need to know first whether the flow is turbulent or laminar in each side, and then based on the type of flow, we can go to the right equation of Nissot number and find out Nissot number. Then from Nissot number, we can find the heat transfer coefficient H. So first of all, we need to find the Vm, the velocity. And this is similar to the previous question. We have to find the cross-sectional area of the tube, AC. So this is the tube, inner tube. It's quite easy, just need to know the diameter of the tube, D. So D here is 2 centimeters. You can find D from it. Reynolds numbers of the water passing through the inner tube. We apply the equation of Reynolds number here. And then we find Reynolds number is 53,490. Again, it's much bigger than 4,000 limit. Therefore, we have turbulent flow. So for this turbulent flow, Nissot number is following this equation. And again, we use 0.4 here because we are heating the water. So heating process, we use 0.4. Then from this, we can get Nissot number. Then it's quite easy to find H following this equation. Now, once we know the H, we can find, of course, the heat transfer, overall heat transfer coefficient if we find H of the oil also. So now to find H of the oil, we follow the same procedure we used with the water. The only difference here between water and the oil actually passing in between. So this is water here, while the oil is passing in this region, in the space between the inner tube and outer tube. So the diameter of this passage here for the oil is not the complete diameter of the outer tube. It's D out minus the D in inside, because we have two diameters here. The space that the oil fills is only this space. And therefore, we have to exclude the inner tube from it. So as you can see here, this is our DH. the hydraulic diameter for the annular space. And we can use now this DH in our calculation to find Reynolds number. So same thing we're gonna do here for the velocity, because we need to find here a cross-section area. The cross-section area is the area of the oil, the annular space, which is the space here shown in red. So this is the space that we need to find. Again, this area is the total area of the outer diameter minus the area of the inner diameter to get only the red area. Okay, and therefore use this area as a cross-section area of the oil and find out the velocity of the oil. And you use this velocity to find real number of the oil, and you can see that R of the oil is very small. It's much smaller than the 4,000. Then this is laminar flow. And you can see here, the value R is quite small because oil actually has high viscosity. It's a thick fluid. And because of this, we expect that the flow is, the speed is lower. If you compare the speed between the oil or the water, if you go back here, you can see here the viscosity of water is much lower than the viscosity of the oil. And therefore, this will affect the RE. So you can see the Reynolds number is very small, 637, right? So comparing these values or check this value with the limit, we find that it's laminar flow. So for laminar flow, we have different formula to find Nusselt number. We can refer to this table. This table actually presents the Nusselt number for laminar flow based on the ratio between the inner and outer diameter of the tubes of the heat exchanger. So if I follow this, and I know that we are in constant temperature case, because in heat exchanger we have constant temperature case, surface temperature is constant. So we follow this column here, and based on the ratio that we have, which is 0.667, it's somewhere here in between. So we have the value of Nusselt number between 5.74 and 4.86. And you will find it that it's equal to 5.45. If we do the interpolation here, you will find that Nusselt number will be 5.45. So use this value in the equation here to find out the heat transfer coefficient. So this equation give me the HO of the oil. Okay. From HO now we can use HO and HI to find U value based on the equation that we have before, and we found that U value is equal to 74.5. Okay. Okay, so this is actually what we need to present in this week. We will continue the remaining topics in week 12. You will have on Friday, you will have lab session, practical session for the boarding gauge test and also for the heat exchanger test. So you will use these formulas, actually use this analysis in your practical. So please come to the practical class and try to understand the principle of each heat exchanger and to analyze the data that you will collect and then submit your report in the next week. Thank you for listening, and hopefully we will meet you again